Thank you. Thank you. So, good day, everybody. So nice to see you all again after the holidays. And it is my pleasure to welcome today's speaker, Dr. Shane Farnsworth of the University of Regensburg. Shane obtained his bachelor's degree in physics from the University of Newcastle and master's from Perimeter Institute for Theoretical Physics. This was followed by a PhD, also from Perimeter, under the supervision of Latham Boyle. Shane was then a postdoctoral researcher at the Max Planck Institute of Gravitational Physics, where he continues to be associated while holding his current position at Regensburg. Shane's principal research interest has been in Cohn's noncommutative geometry and its relation to the standard model of particle physics. More recently, he has pursued its generalization to non-associative geometries with some very interesting and important results. Shane also hosts the charmingly named podcast Escape Sapiens, which I encourage you to watch and enjoy. And today we'll hear from Shane on his recent work on non-associative spectral triples. Over to you, sir. Nice to have you with us.
Thank you for the invitation. So, yes, today I want to introduce some objects that I've been interested in for almost a decade now, actually. This is non-associative spectral triples, so a generalization of Cohn's non-commutative associative spectral triples. And they're very interesting for modeling a number of different physical systems geometrically. So for instance, you can model the internal geometry of gauge theories with exceptional symmetry. And they're also very useful for modeling gauge theories which have constraints. So for instance, if you're interested in Majorana spinors, there's a very nice construction of Majorana spinors in the non-associative special Jordan setup. But I'm not going to go into too much into why you should be interested in the non-associative case. I'm going to assume, given the people who are in the meeting, that you're all interested in non-associative structures. And so what I want to do, what I want to focus on today, is showing you actually how to build these things. Because for many years, I couldn't build these things in full generality. And in the last couple of months, last couple of years, I've made a huge amount of progress such that I can really construct some of these objects. And so the goal today is going to be very simple. I'm going to be showing you how to do it. What is a non-associative spectral triple, and how do you build these objects? And how do they correspond, roughly speaking, to gauge theories, or the internal geometry of gauge theories? Okay, so I'm going to start off, I'm going to separate my talk into two main parts. In the first part is separated into two subsections. I'm going to, as a brief review, tell you what spectral triples are. And then I'm going to give you, again, a review of the associative case, just a refresher, and explain, I'm not sure what the background is of most people, but this should give you some idea of what the objects are that I'm actually talking about. And then the second half of my talk is going to be separated into three examples. And I'm going to introduce the non-associative spectral triples, non-associative geometries in terms of examples. And I'm going to start with special Jordan non-associative geometries. Special Jordan algebras are special because you can construct them by symmetrizing associative algebras. And so special Jordan non-associative geometries and special Jordan spectral triples are very closely related to their associative counterparts. And for that reason, people tend to think of them as not being particularly interesting. But it's in this very simple setting, which is very intuitive, that many of the properties arise, or it's sort of a good framework which gives you hints for how to construct the general setup. Okay, once I've introduced special Jordan non-associative geometries, I'm then going to jump into the slightly more complicated case, alternative geometries. So I'm going to look at discrete octonionic geometries, which correspond to the internal geometry of a G2 cross G2 gauge theory, for example, or G2 to the n gauge theory. And then finally, I'm going to look at a much more difficult case, which is the exceptional Jordan geometry case. All right, so to start with, what are spectral triples, and what's associative non-commutative geometry? All right, so what are spectral triples? almost always when you sit through a talk about spectral triples, you're given some very mathematical definition, and it's sort of a shame because here we're talking about geometry. So these objects should be really intuitive, right? There should be a very intuitive picture that you can grab onto and really understand as a physicist. And so that's what I'm going to attempt to do now. I'm going to attempt to give you sort of the intuitive picture of what these things are. So let's say, for example, you wanted to construct a geometric description of the standard model of particle physics. How would you go about doing that? Well, to start with, you should really look at the model itself and try to infer from the model what the internal structure of the geometry should look like. So here we're talking about some geometry which has some external spacetime, which is we're familiar with. And then at each point in spacetime, we have some internal geometry which describes the particles in our theory. Right? It encodes information about the particles in our theory. So that's the sort of setup that we're interested in constructing. And to get some intuition for what that geometry might look like, yeah, we can look into the standard model itself and see what it looks like. So here I have on the screen the Lagrangian, or at least the fermionic terms for the standard model Lagrangian. And there's a very interesting feature of this part of the Lagrangian that you may not have considered yourself. Right, so here in the top line, we have kinetic terms for the fermions. And the second line has the Higgs terms, the Yukawa couplings. Right? And if you look at this first line, what you'll see is that I've expressed everything in terms of Weyl fermions. So we have our left-handed and our right-handed fermions. And if you focus just on the kinetic terms, you'll see something very special occurs. The left-handed fields are coupled directly to the left-handed fields, and the right-handed fields are coupled to the right-handed fields. So we have the left-handed quarks coupled to the left-handed quarks, the right-handed up quarks with the right-handed up quarks, the down-handed right quarks with down-handed right quarks, the left-handed leptons, and so on, right? There's no coupling with the kinetic terms between the left and right, no direct couplings. Right? It's only in the Yukawa couplings, or the Higgs terms, that this coupling between left and right sectors arises. Right? And so the upshot of this is if you were to extremize the action and you look at the Dirac equation, for example, for the leptons, if you were to ignore the Higgs sector, right, if you ignore these off-diagonal terms, then what this would look like is a decoupling of the left-handed and right-handed fields at the level of the Dirac equation. Right? So you can imagine a universe in which there were no Higgs fields. And then if you just focus in on the Dirac equation, what this would look like is almost two universes. You have a universe of left-handed fields and a universe of right-handed fields. And then there's a bridge between them, which is the Higgs fields. Right? So this sort of geometric picture arises, or this intuitive picture arises. I haven't told you much about the internal details, but you might develop this intuitive picture of a two-sheeted universe where there's Higgs fields which bridge the two sheets. Right? And then the question is, how do we describe this mathematically? Right? Because we know Riemannian geometry, and we're very familiar with it, but Riemannian geometry is more suited to describing these sheets, these individual sheets, not this discrete internal part of the geometry. And so what would be good is if we had some generalized notion of geometry which was better, or it did a better job of describing this sort of a structure. Right? So this is where spectral triples come in. So in compact Riemannian spin geometries, there's a beautiful correspondence that is due to Elaine Kohn, which says that on the one hand, you can describe these geometries in terms of spectral triples of data, where you have an algebra, right? The algebra encodes topological information. You have a Dirac operator, which encodes metric information, and you have a Hilbert space in which they're both represented. So you have a concrete representation, not just some abstract objects. And so on the one hand, you have spectral triples. On the other, you have familiar manifold and metric data. And in this case that we understand very well in Riemannian geometry, or compact Riemannian spin geometry, you can go back and forth between these two descriptions of the geometry. Now, the reason why that's interesting is if you look at the standard model, then these ingredients arise. Right? We have a Dirac operator. I've already shown you this object here. We have a space of matter fields. And we don't directly have an algebra, we have a gauge group. And so you can use the gauge group to infer the existence of an algebra, where the gauge group appears as the symmetries of that algebra, right? So the idea is, at least if you squint, you look at the standard model, and you have the objects that appear in this sort of spectral triple description of geometry. And so the question arises, so if I have these objects, they sort of sit naturally in the standard model, can I understand the geometry that's associated with these objects? And what do I mean by that? Well, to build a geometry, you don't just want to have these objects here. You also want rules of calculus. So you want to be able to describe things like orientation and integration and curvature and these sort of objects. And so you look at the standard model and you see you have these objects that sort of look like a geometry. So the question is, what does the calculus associated with that geometry look like? And you don't get that from experiment. The way you build up the actual rules of the geometry is you look at the cases that you're familiar with, which is Riemannian geometries, and you sort of import the rules of calculus from those geometries into the non-commutative spectral triple setting, and you try to describe in that way the geometry of the standard model, and you try to infer things about this geometry. Okay? And the reason why you should be interested in this is because in some geometric description, the hope is that the rules of your geometry will constrain the theory that you're looking at. So maybe you'll get answers as to why you see the particular gauge group, or why there are three generations and so on. That's the dream, which has not been entirely realized, unfortunately, but that is the initial dream, and why you should be interested in spectral triples. Okay, so that's a basic sort of physics introduction of what these objects are. And now I want to show you specifically how you construct them in the associative case, right? So if you imagine this setup again here, we have some spectral geometry described in terms of a spectral triple, where you have some external space-time, which we understand very well. And then we have some internal part of the geometry at each point. And we want to understand this internal geometries. And so what we can do is we can focus in on that internal part of the geometry and throw away the external space-time, and just zero in and look at this discrete internal space. And so that's what I want to look at building now in the associative setting. Okay, so in a spectral triple, these are the objects that describe your geometry. You have an algebra, which holds topological information, and a Dirac operator, which holds metric information, and they're represented on some Hilbert space. And for a discrete geometry, a discrete internal geometry, what you want is a non-simple finite-dimensional algebra. So you can think of this as a matrix algebra, which is constructed as the direct sum of matrix algebras, right, with, say, n plus 1 factors. And the reason why you can view these as being associated to a discrete geometry is because if you look at the sum and product, then these sort of act component-wise. They're sort of point-wise sums and products, right? So if I take some element of my algebra A and some element B, I form their product, then you take the product in each component individually, right? There's no mixing between the factors of the algebra. And similarly for the sum, right? So in this sense, this algebra corresponds to some discrete geometry where each of these factors sort of encodes topology of each of the points in your geometry. That's the basic idea. And you represent these algebras like this on some Hilbert space. And in the associative setting, you can really think of this as a matrix algebra. And so you have some very nice big block diagonal representation of the algebra, right? And then what is your Dirac operator? Your Dirac operator is some big matrix with off-diagonal terms, right? And as before, we have this two-sheet picture, right, where if you focus in on a point in the manifold, you've got sort of a left-handed point and a right-handed point, and the Higgs field couples those 2 points. That's what the Dirac operator does in this internal geometry, right? So you have this discrete geometry described in terms of a non-simple finite-dimensional algebra, and your Dirac operator has off-diagonal terms that couple these elements together. Otherwise, they'd be completely separate, right? And the Dirac operator contains information about the distance between these points, which is sort of encoded in these parameters here. Okay, so this is the elements of a spectral triple, which describes a discrete internal geometry. And as I told you, to do geometry, you want to also do calculus. You want to be able to describe change and you want to do integration and these sorts of things, right? So, and also at the end of the day, you want to build physics, and so you're going to need some notion of calculus to build an action. Okay, and so what I'm going to show you now, spectral geometry is a big topic. I'm not going to be able to touch on everything. And so I'm going to now zero in on the elements of the geometry that are complicated to generalize to the non-associative case. Right? So I'm not going to tell you every part of the geometry. I'm going to focus in on differential one forms and how they're constructed in Connes geometry, because it's these objects that are particularly difficult to construct in the non-associative setting. And if you understand what I'm going to tell you now, more or less the entire construction is open to you. And so this is what I'm going to focus on. So differential forms, they're the objects that measure infinitesimal change, and they're the densities that you can integrate over volumes and surfaces and line elements in the standard calculus that you're familiar with. And we want analogous objects in Connes geometry, right? So I told you we have these spectral triples, and we import the rules of Riemannian geometry that we understand well to these bizarre, well, they're not so bizarre, but they're more abstract geometries in the internal sector of, say, gauge theory. So how do we import the rules of calculus across from the situations that we understand very well? Well, in a Riemannian geometry, you start with your functions on your manifold. So your algebra is your algebra of smooth functions, and you introduce in the Riemannian case, you introduce an exterior derivative, right, which is a first order operator from your algebra to your one forms, right, which satisfies certain properties. Right? It squares to zero, and it satisfies a Leibniz rule or a graded Leibniz rule. Right? And so Connes does the exact same thing. He introduces some derivative operator, which maps you from zero forms, from your algebra to your space of one forms, which act as a bimodular of your algebra. And so this is the construction. You introduce some D, right, which gives you some notion of one forms, but what you want at the end of the day is a concrete representation. You have a concrete representation of your algebra on your Hilbert space, and you want to extend your representation to one forms and ultimately to n forms. And so how does Connes do this? Again, this is the standard associative construction. What he does is he uses the Dirac operator. Right? So he introduces a representation of an exact form using the commutator of his Dirac operator with the representation of a zero form. And he uses the properties of associative representations to then construct representations of more general one forms. Right? So this is Connes' construction or representation of differential forms. And if you're familiar with the language, this is a standard Clifford representation of forms in the Riemannian setting. Right? So what we're doing here is we're extending our representation, which was originally built just for the zero forms. We're extending it to include our one forms by making use of the Dirac operator. So let me show you how this works, just with a simple example. So let's say, for example, we're interested in an SU2 cross SU2 gauge theory, where you have left-handed fields that transform under one of the SU2s and the right-handed fields transform under the other ones. Then the internal algebra would be two copies of the 2x2 complex matrices, direct sum of two copies of the 2x2 complex matrices. You could represent this on C4, right? So I have my block diagonal representation. Then my Dirac operator is some general block off-diagonal operator. And my elements of my Hilbert space I can view as left-handed elements and right-handed elements. There's a Z2 grading on my Hilbert space. And my one forms, I can construct representations of them just in using Connes' formula for how you construct general one forms. Right? And so your one forms are just off-diagonal elements. Right? So the interpretation here is that you have a G2 cross G2 gauge theory where your fermions sit in 2, 0 and 0, 2 representations, and your Higgs fields sit in 2, 2 representations. Right? That's the general interpretation here, and the symmetries are associated to the symmetries of my algebra. Okay, so this is just a refresher of the associative setting and how you can the elements of a non-commutative geometry and how you construct representations of one forms. Now what I want to do is I want to port this across to the special Jordan setting and show you what changes. All right, so special Jordan non-associative geometry. By the way, before I continue, is what I said clear to people, or have I lost everyone in the room?
We're doing good, Shane. You're doing good.
Okay.
Any questions maybe for Shane at this stage? Yeah, Burnt also says all good. So kindly go ahead.
Okay. So let's look at the special Jordan non-associative geometry setting. Um, and to do that, I just want to introduce. I want to explain a little bit more deeply what we did when we introduced this representation of one forms. So when Kohn defines his representation of exact forms, right, like this, what he's really doing is he's introducing a derivation operator from my algebra into the endomorphisms of H. Right, so this is a derivation map from my algebra into the operators that act on H. Right, and so this is a representation of an exact of the exterior derivative, sorry, in the non-commutative associative setup and the discrete setup as well. And you can see that this operator satisfies the Leibniz rule, right? If I act on A times B, where A and B are elements of my algebra, I can write this out using Kohn's formula, commutator of the Dirac operator with pi of A times B. And since this is an associative representation, I can use the homomorphism property to write this out like this. And the fact that commutators act as derivations means that I can write out the expression like this. And so what I have is delta of A times B is equal to pi of A times delta of B plus delta of A times pi of B, where this is the operator product here. Right, so this really does satisfy the properties of a derivation, right, from A into the endomorphisms on H. And the question is whether we can reproduce this construction in the non-associative setup. Okay, so what is the non-associative setup? And in particular, what is the special Jordan setup? So again, we have a spectral triple, right? We have an algebra, a Hilbert space, and Dirac operator. And for a non-associative spectral triple, the idea is that either this algebra is non-associative or the higher order forms are non-associative. Okay, and so what do you get for free? Right? When A is non-associative, what do you get for free? Well, non-associative algebras have symmetries, just like the associative setup, right? So we have, for instance, the exceptional symmetries. They arise as the automorphisms of non-associative algebras, right? So nothing goes wrong here. You still have symmetries of your algebra. And we have very good examples of non-associative algebras encoding topological spaces, right? So, for example, the octonionic projective plane. But there are other examples as well, right? So we know that we can use non-associative algebras as receptacles of topological information, just as in the associative case, right? So you get that sort of for free here as well. And you also have non-associative representations. They exist. Now, it's true that the representation theory for non-associative algebras is way more scattered and less well developed than the associative setup. But you can always represent an algebra on itself. And there is a well-developed language for representing algebras, non-associative algebras in terms of square zero extensions. So all of these elements that you need to construct spectral triples port across from the associative setup to the non-associative case. So you don't really run into any problems here when it comes to the standard elements in your spectral triple. Right, the Hilbert space is just a standard Hilbert space. There's no product on that. So nothing goes wrong there. Your Dirac operator is literally just an operator. It just is the case that your algebra is non-associative and your representation of that algebra will be non-associative. Okay, so what does go wrong? What is challenging? So for people who are familiar with non-associative algebras, you'll know that in general, commutators no longer act as derivations. Right, so before we define this derivation from our algebra into the endomorphisms of H, this is sort of a representation of our exterior derivative, and we did this using a commutator. Right, so since we're dealing now with non-associative algebras and non-associative representations, will it be the case that we can still construct a derivation in this way? The answer, of course, will be yes, but how you actually go about doing that is complicated. And secondly, algebra representations for non-associative algebras no longer satisfy the properties of associative representations. Right? We defined general one forms using juxtaposition of zero forms and one forms, right? Using the standard operator product. We can no longer do that here. So even if we can construct exact one forms, how do we then go ahead and construct more general one forms, let alone higher order forms in this construction? So this is really where the challenge lies, and this is why I'm focusing in on the construction of one forms in con setup.
Hi, can I
Jane,
interrupt you?
yeah, please go
Yeah.
ahead. Please go ahead.
Hi,
Shane,
John.
what do you mean by a non-associative representation? Can you just spell that out?
Yeah. So the representations I'm going to be looking at today are going to be, for instance, the octonions represented on themselves. So I'm going to be restricting attention to that case, but more generally, you can view a representation as being a square zero extension of an algebra. So what I mean by that is if you have an algebra, you can take the direct sum of the vector space of that algebra with another vector space. Then you introduce a left action of the algebra onto that vector space and a right action, right? And then you can view the vector space of the algebra plus this vector space on which you're representing as being a larger algebra, right? And usually for compatibility reasons, you impose conditions like you say, if I start with an alternative algebra, then I ask that this square zero extension is also an alternative algebra.
Okay, so you're not starting with an arbitrary Hilbert space.
Sorry?
You're not starting with an arbitrary Hilbert space.
No.
Okay.
No. Yeah. So just like in the associative case, the representations that you can write down are restricted. Right? You can't write down anything. But there are the cases that I'm going to be looking at. What is particularly interesting about this from the mathematical perspective is that non-associative geometry gives you an amazing setup for understanding non-associative representation theory. So what you'll see as I go through this talk is starting with very simple representations like the octonions represented on themselves. What will be generated is more complicated bimodules over the octonions. I'll get into this in a second, but for the purpose of this talk, all you need to think of is every time I'm talking about non-associative representations, except for in the special Jordan case, which you can do more, just think of the octonions represented on themselves or the exceptional Jordan algebra represented on themselves, and then that should get you through the talk.
Okay, fine, thanks.
Okay, so special Jordan algebras, what are these? So Jordan algebras are algebras which have a product, which is commutative, and which satisfies the Jordan identity. So here, if we look at the product, if we set up the commutator, where the entries are two elements of our algebra, this will always be zero, right? Because our product on the algebra is commutative. Similarly, if we look at the associator, there's a bracket with three entries here. Then in general, associators of general elements will be non-zero, but the Jordan algebra satisfy this Jordan identity, right? So this essentially the ordering of brackets matters, right? And the associator is defined as you act first on the first two terms, and then so the associator of three elements A, B, C will be A times B times C minus A times B times C, where the bracketing there matters. I'm not sure if that's clear, but it should be obvious from this line here. So the special thing about special Jordan algebras is you can start with an associative algebra and symmetrize the product to obtain a special Jordan algebra. Right? So if I start with an associative algebra with elements A and B, I can symmetrize the products between A and B to get a symmetric product which satisfies both the Jordan identity and this commutativity property. Now, the other interesting thing is because I can construct special Jordan algebras from associative algebras, they also inherit representations. So this sort of answers John's question as well. In this special case, you inherit representations from the associative algebra from which you compose the special Jordan algebra, right? So pi of A times B is equal to pi of A times pi of B plus pi of B times pi of A. Right? You inherit this property for your associative representations of Jordan algebras. And this is a very important property that will show up shortly. Okay, so let's look at a two-point special Jordan geometry. So just as in the associative case, let's start with an algebra which is two copies of the 2x2 complex matrices, right? The Jordan algebra 2x2 complex matrices, represented on H4. Right? Now, just as in the associative case, I can construct a block diagonal matrix representation of this algebra. Now, my Dirac operator will just be a general off-diagonal matrix, Hermitian matrix. And again, I can view my elements of my Hilbert space as being separated into left-handed terms and right-handed terms. Now the question is, if I then take my derivation from the standard form of Con's derivation from the algebra into the endomorphisms on H, does this object here, right? Does this operator still act as a derivation? Does it satisfy the Leibniz rule? And so we can check this, right? So we have this derivation map from the algebra, right? So we can act on an element A times B. And we can express this using Con's standard formula. And then we can use the properties of an associative representation of Jordan algebras, right down here, to expand out the right-hand side. Right? And so what you'll find is that I have delta of A times B is equal to half times delta of A times B, the symmetric product, and pi of A delta of B symmetric product. Right? So this looks exactly like a Leibniz rule if the product between zero forms and one forms is the Jordan product, right? Not the associative operator product, but a symmetrized product, right? So in other words, what we're doing is we're forced to extend our symmetrized product from the zero forms to the one forms. Okay, so here's the key first lesson. So let's compare the associative and special Jordan geometries. So in associative geometry, one starts with a spectral triple and defines a derivation map from the algebra into the endomorphisms on H. And this has to satisfy a Leibniz rule, right, with respect to some product. In the associative case, this product here is just the operator product, right? And D can be completely general. So here we're looking at the finite-dimensional discrete setup. And this Leibniz rule here places absolutely no restriction on the Dirac operator whatsoever, right? You just assume the operator product, and this equation holds. In the special Jordan geometry, you start with a spectral triple, where A is a special Jordan algebra. You again define this derivation from the algebra into the endomorphisms on your Hilbert space. And again, this satisfies a Leibniz rule, but now the product here is not the operator product, but a Jordan product, right? So the take-home lesson is, in associative geometry, the product between forms is the operator product. In non-associative geometry, you have to determine a consistent choice. And you'll see that this continues in the more complicated examples I'm going to look at now. All right, so I'll stop here if there are any questions. Is everything clear so far?
So when you say a special Jordan algebra, it is as opposed to the exceptional case.
Mm-hmm.
And
Yes.
the exceptional case is only J3O. Is that correct? Is that the only thing to deal with, Len?
Yeah, so in the exception Jordan case, I'm going to look at direct sums of that algebra that you mentioned.
Okay, thank you.
Yeah. Okay, so there's a question.
Just a brief one. I'm trying to better understand your representation theory. Do you use the linear operator, multiplication operators? I know from non-associative algebra representations that the multiplication operators can be used to represent a non-associative algebra, but your setting seems to be different. Can you explain this to me, please?
So in the alternative case that I'm going to talk about now, that's exactly the sort of representation that I'll use.
Okay.
But in the case of a special Jordan algebra, you can do more with a special Jordan algebra. If you imagine the setup where you just have a matrix algebra, right? A standard associative matrix algebra. So you have the abstract algebra, then you have the representation as matrices. And what you can do is you can symmetrize the abstract algebra, and simultaneously you can symmetrize its representation as
Okay.
matrices, and then you get this equation here. Right, so this is this pi here. It's just taking an object of an element of my abstract algebra and representing it as a matrix. So this is an honest to God matrix on a vector space, acting on a vector space.
Okay.
So you can think of this. So the Jordan algebras I'm looking at here are, for instance, the algebras of n by n Hermitian matrices. So you can think of pi of a times b as just being like it's just some matrix representation of whatever this product is, and you'll inherit a representation from the associative algebra that you constructed your special Jordan algebra from, which just satisfies this rule here.
Okay, to just use the symmetrization of the old standard representation of the matrix algebra.
That's right. That's right. So
okay, so thank you. I had trouble understanding this. Okay.
Yeah. So imagine, you've got a finite dimensional algebra that you represent, associative algebra that you represent as matrices on a vector space. Then symmetrize that representation. That's exactly what I've done here.
Okay. Thank you.
Yeah. Okay. Okay. So now let's look at a more interesting case where we don't have the nice representations of special Jordan algebras. So now let's look at two copies of the octonions represented on two copies of the octonions. Now, this multiplication operation, this representation built from the multiplication operators that was just mentioned, is what I'm going to be using. So for any non-associative algebra, for any algebra, I can construct the left action of an algebra element as an operator acting on the vector space of the algebra. So I have here the left action of A on B is just defined as A times B, where this is the product in the algebra itself. And similarly, I can construct a right acting operator, right? And I can use these to build a larger representation, right? So here I have two copies of the octonions acting on themselves. And so I can build a larger representation of this algebra on H in terms of a block diagonal matrix, right? Where these elements here are just the left action of the algebra on itself. Right? So I have the left action of this element of the algebra on here, and the left action of an element of this part of the algebra on this part of the Hilbert space. And similarly, I can construct a right acting representation. Now, the important thing with the octonions here is the following. In the previous examples that I gave you, I only had left action. Here I have a left action and a right action, but you can always express the right action in terms of left action, in terms of chains of left acting operators. And so really you should think of this as being nice notation. It's very compact notation, but it doesn't introduce a separate representation because the two representations are linked to one another. Okay, and then I want to introduce a Dirac operator. You can think of this space here as just being R16. And so the Dirac operator is just a standard block off diagonal matrix, right? Which I've written in a nice basis. So these EJs form a basis for the octonions. And the star here indicates the dual, right? So this is just a standard linear operator, which is block off diagonal, right? And also you can demand this is Hermitian with respect to the inner product on R16. Okay, so before diving into the calculus that you can build up on this two-point geometry, alternative algebras satisfy a few nice properties that we're going to need. First of all, alternative algebras, like the octonions, satisfy an alternative property, which means that if you take an associator and you interchange any two elements of the associator, you pick up a minus sign, right? Now, what we can do is we can use the left action and right action of our algebra elements on itself to re-express these associators in a nice way. So if I take this associator here and this one here, I can express them in terms of left and right actions, right? Which gives you these identities here. Right? These identities here are just a rewriting of this alternative identity, right? And the reason why this is very useful is it's analogous here to the property we had for the representation on our special Jordan case, Right? Here we have a representation of A times B, which can be written as a sum of products of representations of our operators, right? Where this product is just the operator product. And we have a similar setup here for alternative algebras, where we have the left action of A times B can be written as a sum of products of operators, right? Of course, there's the right action here, but this is just a property of the octonions. There's nothing that we can really do about this being slightly more messy. Okay, and another property of the octonions is that they're an involutive algebra, which means there's an involution, which I'll call J, which just sends all the imaginary elements of the octonions to minus themselves. Right, and this J operator, this involution, satisfies the usual properties of an involution. And we can use this involution to express the right action of the algebra in terms of left-acting algebra elements, right? And in terms of our two-point geometry, where we have our larger left and right actions here, we can introduce a big J to express our the right action of our algebra on our Hilbert space in terms of the left action transposes and this big J, right? This big involution operator. Okay, so this is all that we need now to move on with our geometry. So just to remind you, we
Could I
have...
ask you a question? Sorry to stop you.
Yep.
In the octonionic case, what is it that prevents us from defining the Jordan product as a symmetrized operator product? What goes wrong there?
The product is just different. It's not a Jordan product. So in the special Jordan case, the algebra satisfies these properties here.
Right.
This is a completely different algebra. So it satisfies properties like this, right? And it just means that you have, you don't have the same expression for the representation. You just end up with different equations.
So if I equate these two, I get the LA-RB commutator as equal to the RA-LB commutator, isn't it?
If you equate the sorry, what do you mean?
Yeah, I mean these are both are ways of writing LAB, no?
That's right. Yeah.
So
So on the right hand side, this is equivalent to, so on the left hand side, I have the left action of A times B. On the right hand side, I have the left action of A and the composed with the left action of B, and the commutator of left action of A composed with the right action of B acting on some element. Right? So this equality holds if your algebra is alternative, which is this property here. Right? Which if your algebra satisfies this property. So in particular, all associative algebras are alternative, right? And so this is satisfied by all associative algebras. But in the case of associative algebras, this second term drops out. This is zero for associative algebras. And so you return to the standard homomorphism property that you get for the representation of associative algebras on vector spaces. You just get these two terms here, if you can see my mouse.
okay, yeah.
But
Thank you.
this is a more this is just the alternative identity written in a funny way, in a more useful way.
Bernd has a comment, the octonions form a non-commutative Jordan algebra. Is that
That's right. There are strong links between alternative and Jordan algebras, but I won't get into that. This is yeah. So let's go back to the two-point octonion geometry, right? And what we want to do is we want to construct this derivation map, and we want to show that it satisfies the Leibniz rule. Right? So we construct this map just as in the associative and special Jordan cases. And so we can act delta on A times B, where A and B are elements of our larger algebra, O plus O. And then we can use the properties, right? We can use these rules here to expand out our representation, right? And when we do that, what we find is delta of A times B is equal to delta of A times pi of B. So that looks good. Then we have delta of A times pi r of B. It's not as nice, right? Because this is not represented as the left-handed guy. And then you have D of pi of, the commutator of the Dirac operator with pi, the right acting representation commuted with the left action of B on the Hilbert space. Right. So this is quite a bit more disgusting than in the special Jordan case. But if you squint your eyes, you see that this would satisfy a Leibniz type rule if you had a product between zero forms and one forms, which looks sort of like this, right? So I've just rewritten this term here, down here, and rewritten this term here, down here. So this would satisfy a Leibniz rule if you defined your your left and right products between zero forms and one forms in the following way. Right? Now, what you would want to do is you'd want the left and right hand sides of this equation to contain the same elements. Right? So if you just look at this first line, on this side we have delta of A, and here we have a delta of A and an operator product here, delta of A and an operator product. And this isn't delta of A, this is something else, right? Something else that we would like to express in terms of delta of A. And similarly, here we have pi L of B, and here we have pi L of B and an operator product, pi R of B, right? So not quite the form that we want, and again, pi R of B, right? So what we would like to do is to express this right-hand side of the expression in terms of just these elements over here, right? And so what we can do is we can make use of our big J operator and write our right-handed action in terms of our left-handed action. And then we get a product that looks pretty good, except for these messy terms in here. Right? These messy terms, we'd like to write them as an operation on delta of A. Right? And what you can see is this would be possible if J commuted or anti-commuted with the Dirac operator. Right? If you could pull J through here, then this would just give you some operation on delta of A. Right?
Sorry, what was J? What was J?
So J is an involution operator. Right? So little j was our involution operator, and I've just expanded to construct a bigger J for our representation of two copies of the octonions on itself. Right? So in other words, what would be nice if we could pull J through D? And so if we take a look at our Dirac operator, you notice that we can separate it into two parts. Right? You can separate it into D plus and D minus, where D plus is just composed of the real parts of the algebra, and so completely real parts and completely imaginary parts, and D minus is a mix of real and imaginary parts. Right? And if you decompose D in this way, you'll see that D plus and D minus either commute or anti-commute with J. Right? And the way to see that is if you act from the left with J on the real elements, you don't pick up a minus sign. And if you act from the right, you don't pick up a minus sign. If you act on terms like this, from the left, if you act, you pick up a minus sign acting on these imaginary elements. And similarly, if you act from the right, you pick up a minus sign. Whereas the opposite happens here. If you act from the left over here, you get a plus here and a minus here. If you act from the right, you get a plus here and a minus here. Right? So you end up, you should be able to see that if you separate the Dirac operator into these D pluses and D minus, you end up with terms that either commute or anti-commute with J. Okay, so what we can do then is we can restrict D to be of the form D plus or minus. Right? So if you do that, then this product, right, you can rewrite these terms here in the following nice way. Right? You can express these terms completely in terms of delta of A and pi L of B. Right? You'll see that these terms appear exclusively on the right-hand side. Right? So this works. So what we can do is we can define general one forms, and we can define a product between zero forms and one forms in the following way. Right? So this is just this product that we've defined here. Right? Just written out for a general one form. And if we define this product between zero forms and one forms, then indeed our delta operator does act as a derivation. It satisfies the Leibniz rule with respect to this product. Right? So this is introducing a new bimodule structure over alternative algebras where we have this complicated action of algebra elements on the bimodule of one forms.
Sorry,
Okay.
could you repeat use by restricting to D plus minus, you mean work either with D plus or with D minus? Is that what you mean?
Yeah, so what would happen is if you impose if you so what if you reverse the logic, what would happen is if you demanded so we start with the story is as follows. If we had started with this two-point geometry,
Mm-hmm.
right? And then we demand that zero forms and one forms have the following product,
Mm-hmm.
where we have this plus and minus here, and here's the
Mm-hmm.
form of a general one form.
Mm-hmm.
Then what you would find is this would force you to take, so if you selected, for example, the case in which this is a minus here, that would
Mm-hmm.
force you to take a Dirac operator, which is d plus of this form.
Mm-hmm.
I went backwards. The logic was backwards to get there, but so the key lesson number 2 is the following. In associative geometry, one starts with a spectral triple and defines this derivation operator from the algebra into the endomorphisms on H. And this satisfies a Leibniz rule with respect to the operator product, where D is unrestricted. In the non-associative case, you start with a spectral triple, you define this derivation, and again, this derivation satisfies a Leibniz rule, but with respect to a new product, right? And what you'll find is that the pair star and D, so your choice of product and your choice of Dirac operator, they're coupled, right? This is also true in associative geometry. It's just not obvious because you always take you always take the product between zero forms and one forms to be just the operator product. And that places no restriction on the Dirac operator. But more generally, when you define a spectral triple, you also have to define these properties. This is sort of swept under the carpet in the associative case. You don't notice it. All right, so for a spectral triple, the choice of the star product between zero forms and zero forms, zero forms and one forms and two forms. You have a star product at all orders. This choice is coupled. Your choice of product and your form of the Dirac operator.
Can one see, okay, form a picture of what D plus and D minus are doing? Maybe that's what you're telling now.
Yeah. So I'll give you the physical interpretation here. So if you look at the spectral triple that we just constructed, this is a spectral triple that corresponds to the internal space of a G2 cross G2 gauge theory, right? The symmetries are the symmetries of the algebra representation. So you have two copies of the octonions, and so the symmetries of one copy would be G2, and the symmetries of the other copy would be G2, right? And so your Higgs fields are these. You end up with off-diagonal Higgs fields, right? And this term here is a Higgs field that when you fluctuate the Dirac operator, you'll end up with a Higgs field which it sits in the 0, 0 representation and the 7, 7 representation, right? If you take D plus, so here's D plus. And the left-handed fermions will sit in the 0, 0 and 7, 0 representations. The right-handed fields will sit in the 0, 0 and 0, 7 representations. If we had taken D minus, then we'd end up with Higgs fields that sit in the 0, 7 and 7, 0. So that's the physical interpretation. It's very similar to the associative case, except the objects are slightly more complicated. Okay, so that's the special Jordan and the alternative case. So now I want to describe a much more complicated setup, which is the discrete exceptional Jordan geometry case. But I'm going to make it simple. So again, we start with a two-point space, right? Just as in all the other setups. This is exactly the same, except now we have two copies of the exceptional Jordan algebra acting on itself, right? And the Dirac operator is a standard linear operator acting on this large vector space, which is block off diagonal. We use the left action of the algebra on itself to construct our representation. And again, we can split the elements of the Hilbert space into sort of left-handed fields and right-handed fields, or left-handed elements and right-handed elements more correctly. Okay, so now here's the reason why the exceptional Jordan algebras are so much more complicated than the special Jordan case and the alternative case. So in the special Jordan case, we inherited a representation from the associative representations, right? And we had a nice expression. I should show you the expression again. Right? We had the inherited representation, so we could write pi of A times B in terms of a sum of operator products of pi of A and pi of B. right? And a similar thing happened with the alternative representation that we looked at previously. In the exceptional Jordan case, that's no longer the case. As far as I know, there's no nice expression we can write here on the right-hand side, which is expressible in terms of a sum of products of pi A and pi B, right? And so because of that, we can't use such a product to derive the product between zero forms and one forms. Right? So how do we...
Sorry, a naive question. The exceptional Jordan case is not even alternate associative. Is that true?
So the special Jordan, the exceptional Jordan case, again satisfies the standard properties of Jordan algebra. So it again satisfies these standard properties here. The only difference for the purpose of this talk is you can no longer construct it by symmetrizing an associative algebra. Right, so you can think of the 3x3 self-adjoint octonionic matrices equipped with a symmetrized product. That's an exceptional Jordan algebra. And I'm also going to look here in this example geometry.
No, I was comparing it with the alternate associative case O plus O that you just described. What's the difference between that and J3O?
So J3O is the algebra of self-adjoint 3x3 octonionic matrices, which is equipped with a symmetrized product. So you've got sort of a matrix, an octonionic valued matrix. That's what your elements look like. And you take the matrix product, which is symmetrized, and internally you have the octonionic product component-wise.
I think Bert is addressing my confusion. The exceptional Jordan algebra is not alternative, but power associative. Yeah, that's what I was confused about. Yeah. No, it's not alternate associative, but power associative.
Yes, and
that's right.
And it satisfies the Jordan identity, which in the commutative cases leads to power associativity. But in the non-commutative case, it's more strict than power associativity, but the exceptional Jordan algebra has the commutative product, so it's power associative. And sorry for interrupting.
No, that's all right. This should be more of a discussion anyway. I think this material that I'm going through is quite alien perhaps to a lot of people, so I'm very happy for people to jump in. Okay, so we no longer have at the level of the zero forms, we no longer have some nice expression expressed in terms of sums of products of representations of our algebra elements, which we can use to derive a product between zero forms and one forms. So how do we make progress? Well, here, right, lesson 2, for a spectral triple, the choice of star product and D is coupled. So let's just make a choice. So let's assume that the form of the star product between 0 and 1 forms is just given by this associative form. Right? So pi of A times omega, where omega is a 1 form, is just pi of A times pi of omega, where pi of omega is just the standard block off-diagonal form. Right? And then let's check the Leibniz condition. So this is the Leibniz condition, right? We now know what the product is between zero forms and one forms because we've enforced it to be this. And then we can just check this expression. And so we can write it out. So the left-hand side, this is just a standard linear operator, right, which we can write in this form here. You can brute force calculate it. It's just 1 or 2 lines. And the important thing is here we have to calculate. You do have to worry where these brackets are when you calculate each term. But after you've calculated them, then this is just a regular operator. Okay, but so for this expression to hold, for the Leibniz condition to hold, then the left-handed side minus the right-handed side has to be equal to 0. And so we can write down left-handed minus right-handed. And when we do that, we get this expression here, right? Which is written in terms of these associators here. So each of the terms has an associator in it. Now we want this to be equal to 0, and this has to be equal to 0 for any element B and any element A. And so what that tells us, the only element which associates with all elements A and B is the identity element. Right? So this forces our Dirac operator to be composed only of identity elements. Right? Right? So we enforced this choice of bimodule structure for the one forms, and that placed restrictions on the Dirac operator. And so the physical interpretation is here you end up with the internal geometry of an F4 cross S4 gauge theory with uncharged Higgs fields, left-handed fermions sitting in the 0, 0 and the 26, 0, and right-handed fermions or germions sitting in the 0, 0 and 0, 26 representations. Okay, so
This would work also for E6 cross E6?
yeah, so for E6, you'd have to take a different algebra, and that algebra would be a Brown algebra. What's known as a Brown algebra. So you'd take two copies of the Brown algebra acting on itself. Now, all of the examples I've shown here are like F4 cross F4, G2 cross G2, but that's just because they're the simplest models. You can build more general constructions as well. I've just picked out the simplest things to make the discussion as digestible as possible. But okay,
it'll work there. It'll work there.
Yeah. You can construct E6 cross E6 models.
Right? Okay, great. Thank you.
Okay, so that's all I wanted to discuss today. So I wanted to focus on the parts of the geometry that are most difficult to construct. So the construction of one forms. So if you've sort of absorbed a little bit of what I've said, then you really should be able to go away and construct these geometries yourself. And so what I want to say is the following. The main challenges of doing non-associative geometry are solved. This is something that I've been looking at, working on and solving now for years. And in the last months or couple of years, the formalism has really come together. We really can now construct finite-dimensional, discrete, non-associative geometries, right? And there's an enormous amount of low-hanging fruit, right? So if you find this sort of thing interesting, many of the results from associative non-commutative geometry have immediate and direct analogs in the non-associative case, right? So that's an interesting direction to go down. And now there are many physical models that were out of reach of the associative setup, which are now accessible in the non-associative setup. So for example, you can look at exceptional Jordan algebras, Octonian models, Bayesian algebra models, Brown algebra models. There are very interesting models that you can construct. And the reason why this is interesting is that many people are interested in looking at, for example, the exceptional Jordan algebra and trying to find the representations of the center model in that algebra. And there's a lot of people working on this sort of thing. But often people playing around with these algebras, they just look at the representations. They don't have dynamics. What this does is it gives you dynamics for these sorts of models. Right? If you can construct your model as a spectral geometry, then you get access to the spectral action. And so for people who are interested in looking at the representations of complicated algebras and trying to reproduce the standard model, this gives you a tool to actually construct dynamics in those cases. Thirdly, this provides a brand new environment for exploring non-associative representation theory. So I didn't really use the words, but when we construct these products, right? So we constructed, these complicated products. Really, what you're doing is you're taking, you're forming a product between the octonions and a bimodule over the octonions. So this defines a new bimodule structure that I think is unique in the literature, or it's new in the literature. And these sort of pop out of the formalism, right? So you start off with very intuitive representations of the octonions on themselves, and for free you get these very interesting new representations of the octonions that I've never seen before, and these carry the representations of the octonions, and they're very interesting in many ways, and we can discuss those if people are curious. But so what this does is it gives you a physical environment, a very physical environment it gives you a very physical environment for exploring non-associative representation theory. And finally, it gives you a brand new environment for constraining the rules of spectral geometry, right? You saw that in the associative case, your choice of product between zero forms and one forms was always taken to the operator product. It was just obvious that's the thing you take. What non-associative geometry does is it pushes the formalism to sort of its breaking points where internal consistency conditions become obvious. And so it's a really nice language or environment for exploring the rules of spectral geometry. Right, so there are infinitely many interesting ideas to explore that are completely unexplored because this is, it's a new branch or sub-branch of geometry. So yeah, anyway, this is all I wanted to show you today. I hope it was understandable. So thanks for listening.
Yeah, great, great. Thanks, Shane. It was beautiful and insightful, very enjoyable, something one wouldn't know unless one heard you. So very curious, quick couple of questions. So what's a Bison algebra?
Bison algebras are really interesting. They're like the octonians, so that it's an eight-dimensional algebra. But so it's a normed algebra and it's a division algebra that's not the octonians, but the norm is quartic, not quadratic. And the thing that makes it interesting is it doesn't have G2 symmetry. It has SU2 cross U1 symmetry, and it carries the representation of the leptons. So it's an algebra that has chiral symmetry and the symmetries of the electroweak sector. And
That's great, yeah. But
yes,
coming from the octonions.
it's very similar to the octonians. The construction is very similar. I'm not going to reproduce it here because it's not at the back of my mind. But the point is the following. This is a point that people don't absorb when it comes to non-associative algebras, and it's one of the most important factors why you should be interested in them when you're modeling physical systems. If you look at the finite-dimensional associative algebra case, commutators act as derivations. So take any element of your algebra, form a commutator of it with it, and that object will act as a derivation. That means that every element of the algebra acts as a generator of symmetry on every other element. So in general, you don't get chiral symmetries in associative algebras because everything transforms under everything, right? You don't get this separation to left-handed and right-handed and this sort of thing. If you look at non-associative algebras, the bracket no longer, the commutator no longer acts as a derivation. And so not every element acts as a generator of symmetry on every other element. And so what you can find is you can find algebras which have chiral representations of their symmetries. You can find, I mean, this is one of the most interesting aspects of playing around with non-associative algebras that isn't really appreciated.
Do you have to go to the Bison algebra, or your F4 cross F4 also is chiral?
It's not chiral. So F4 cross, well, F4 plus F4 is chiral in the sense, in the weak sense that it's sort of a discrete, it's a non-simple algebra which has sort of a one part that is closed under the symmetries and another part that's closed. But I mean, if you look at a simple algebra, you can find simple algebras that have just one factor, which are chiral. That's the unique thing.
But I want both the chiralities. Say E6 cross E6 would work, or I have to go to the beyond that.
You can get E6 cross E6. Yeah, in that case, the simplest model would be you take two copies of the Brown algebra.
Right, and ascribe different opposite chiralities to them.
Yeah, I mean that'd depend on the actual model that you constructed, but that's the path you would go down if you wanted to build that particular sort of model.
Great, thank you very much. I have other questions. I'll come back to it, but Bernd, you go ahead, please.
I just a note. The Brown algebra is actually hard to find in the literature, so if you want, I can give you a link to it. There's a nice paper by Skip Garibaldi, I think it is, where he goes through the Brown algebras. So you could even just Google Skip Garibaldi and Brown algebras, and you might find it.
You could kindly leave it in the chat. We could all.
I don't have it on hand.
Yeah, no problem. I remember Garibaldi. Yes, thank you. Bernd, please go ahead.
Thank you very much for this nice talk, and congratulations to your accomplishments in advancing pure mathematics along the way by developing new mathematical tools. I have a question concerning the structure of your Dirac operator. Do you form tensor products of octonian elements with themselves and of exceptional Georgian algebra elements with themselves? Is that correct?
Yeah, so this is something that I sort of skipped over. So if you look at this case, right, where we have two copies of the octonians.
Yes.
So this is a normal vector space on this side. You can think of it as just being R16,
Mm-hmm.
right? And you can write out a basis for that vector space, right? You could write so really you could have like you could call the basis of this vector space E subscript I. Its elements
Mm-hmm.
are E subscript I, and you could have a superscript that tells you which of these octonionic elements it belongs to. That's sort of what I'm doing here. This is a normal linear operator. I'm just writing it out in terms of the basis elements of each of these copies. So this octonionic element, you can write it in terms of the basis of real and imaginary elements, which I
Mm-hmm.
call EIs, but they're just vector space elements. They're not. There's no product in the vector space. So
Okay.
this is an honest to God standard linear operator. I've just expressed it in terms of the octonionic basis that you're familiar with. And the reason why that's useful is because you know how the left action acts on these elements, right? Sort
Okay.
of,
So
then
just
this, yeah.
for better understanding. So this is these are the basis elements of the octonions. So the additional imaginary units you have in the octonions compared to complex numbers.
Um, well, so in this vector space, this is just R16. This is isomorphic to
R16. Okay,
R16.
okay, okay. Now,
And
okay.
and so for the octonions, you can put sort of an inner product on them. So if you take two elements, A and B, and you take
Mm-hmm.
the involution of A and multiply with B, and then take the trace of that, and the trace just pulls out the real element.
Mm-hmm.
That's the standard inner product on R8.
Okay. Okay.
And so this here has this is, you can think of this as R16 with a standard real inner product.
Okay. Okay.
And this Dirac operator is Hermitian with respect to this inner product.
Inner product on R16. Okay.
That's right. That's right.
Okay, okay, thank you very much. This really helped me to understand your construction. And I have only one simple additional question, and then I will stop. How general is your construction? Can I also use this for, let's say, the algebra of 4 times 4 Hermitian matrices over the octonions?
It's completely general.
So
Um,
then in
it
principle, you
just
can, yeah, sorry.
yeah, it just becomes increasingly disgusting. Um, so
Okay,
I mean, the construction that I built for the exception Jordan algebras, I used a trick, right? I enforced this product between zero, like this was input. I enforced this product. You could take the 4 by 4 octonionic matrices, and you can do the same thing. You can enforce this product, and what you would almost certainly find is that you would get a Dirac operator of this form again. I don't know what the
okay.
symmetries would be because I don't know what the symmetries of that algebra would be.
The
But
symmetries are G2 times SO4.
okay. So this is, yeah, okay. Yeah. So you definitely can do this.
Okay,
But in that case, you'd have to the tricky thing would be defining sort of a product between zero forms and one forms. The
okay,
examples that I've given you here are sort of nice examples where this is where you can do the calculations. You can definitely build the constructions you want. They're just going to be really difficult. They're technically difficult to implement. They're not
okay.
impossible.
Because in the
Um,
case of the 4 times 4 matrices, Hermitian matrices over the octonions, they are no longer power associative, hence my
mhm.
question. But if your setting is so general, then one could also explore non-power associative algebra, something which has not been done in detail. Would be
Yeah,
interesting.
you definitely can, as long as you have. I mean, you still need to construct your Hilbert space. You need to have some sensible notion of Hilbert space. But then, yeah, this is a
This,
very general construction. There's
okay,
one thing that I want to point out is, um, so there's something very special about associativity, which that if you have an element of your algebra which associates with all other algebra elements, right? So if I have an element like the identity element, then commutators of that element with anything else will act as derivation elements, as generators of symmetry, right?
okay,
So in other words, build an algebra, find an element of that algebra which associates with all other elements, and then you can build derivations using that associative element
Okay.
using a standard commutator. And that's what's happening here. So this Dirac operator, it's composed of identity elements which associate with everything. And so this object here, even though the algebra is really associative, this is the trick I've sort of swept under the rug here.
Okay.
Because this is so you can do this with any non-associative algebra. Because this object here is composed of elements which associate with everything, this will work as a derivation element when you just use this with you construct a commutator using this element, because it essentially associates with everything, from the left and from the right. This operator. So yes. So basically, what will happen? This is sort of an interesting thing in non-associative geometry. In non-commutative geometry, because commutators of any element act as derivations on any other element, what ends up happening is you get gauge theories which have too many Higgs fields. You have to explain why you don't get all these different Higgs fields in your construction, because any operator is a good derivation operator, and so you have to work hard to explain why those operators don't arise. In the non-associative case, you have the opposite problem. It's really, 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 really difficult to find a Dirac operator that works. And so the point is that you can start with a non-associative algebra and you can impose a product between zero forms and one forms like this. But usually what happens if you do that is you end up with an uncharged Higgs field at the end of the day that's composed of just identity elements, because it's an operator of this form which will associate with everything. But at the same time, because it associates with everything, it also doesn't really transform it or anything. But yes, so that's a very long answer to your question. Yes, you can do what you want to do. It's going to be really tough.
Gonna be tough, but at least it's possible. I mean,
Yeah,
not impossible.
it'll be possible, and it'll be hard, and probably there's a so this is the thing. When I was building these geometries, I mean, everything I've said might be very obvious to you in hindsight, but when you don't have a path to go on it, it's really difficult to work out, what are the objects that you're playing with. But so now, if you follow this talk, you sort of know the objects that you're playing with. The tricky thing is working out how they interact with each other, like working out what these products are and things like this. But you at least have the guardrails for what you're looking for.
Okay, so then I finish again with an impressive accomplishment.
Thank you.
Veselin, go ahead, please. Thank you, Bernd. Veselin, go ahead, please.
Thank you, Shane. Thank you very much. Very interesting talk. I'm trying to make sure that I understand your talk in the framework of differential geometry and then extending it to more complicated structures. Usually in differential geometry, we have functions and derivatives and tensors. And the thing is that very often the rule of differentiation is very clear. I mean, on a function, you derived dx would be the differential, but this is effectively the basis for the differential one forms. And then what you have is your algebra is kind of a direct product of the algebra and the basis, and that forms the whole vector space of one forms. In the usual kind of simple differential geometry, basically you apply the usual multiplication when you try to act with a zero form on one form. You're just acting with the parts that is containing the elements of the functions. But when you move to more complicated differential geometry where you introduce covariant derivatives, now it becomes a little bit trickier. Basically, now when you do the differentiation, you actually have to rotate your basis also. So these are the parts of the connection form that you would introduce. So taking this to what you are representing, I mean, it seems to me you would like to maintain the algebra homomorphism through the construction as much as possible, and then you come to the point where now you have to figure out what would be the Dirac operator that would be equivalent of differentiation. And the idea there is that it has to actually, in a way, related to commutator, because this is a natural extension of differentiation with operators. But then what you're facing is the question, how do I extend the action of the zero form on my one form? And now, coming back from the covariant derivatives, basically there's usually a statement in Riemann geometry saying, well, you can pick a basis where there's no rotation of your basis form, basis vectors. So in a sense, I can say, well, let me pick this, what you are just showing actually, I think, on this one. I picked the choice that I act with 0 forms on one form in a trivial way, which preserve the algebra homomorphism, but I don't rotate the one form basis. And then this seems to constrain so much things to the unique Dirac operator, which is kind of coming on the original case where in the usual differential geometry, basically you don't have much choice. I mean, once you pick that there's no rotation of the basis, then the differentiation of the function is clear. Is that the case here in a sense? And
I'm surprised that you've said it so clearly.
Okay, thank you.
No, that's exactly the case. So the language that you would use in noncommutative geometry or spectral triples is you'd say that the Dirac operator here doesn't fluctuate. So usually there's a prescription where you start with the Dirac operator and there's a way of replacing it with a covariant derivative or some analog. And here, the Dirac operator, just it doesn't have any interaction underneath the symmetries. So that's exactly what happened.
So then, if I go backwards, if I pick actually a different Dirac operator, which doesn't match the one that canonically would be constructed, it's similar like, well, I pick a covariant differentiation that doesn't match partial differentiations, then I have to go and modify how I rotate my basis. So I have to actually introduce change in how the 0 forms act on one forms to be consistent with this new Dirac operator.
Yeah, that's right. So that's the interesting bit of the story, which is that so you could have gone the other way, right? So here this lesson here where you have so this coupling between the bimodule action and the Dirac operator or the derivative operator. So yeah, that's you could have gone the other way. You could have you start with a representation of your algebra on the Hilbert space, and then you say, I want this Dirac operator. I want it to transform under the symmetries of the algebra in this particular way. I want it to sit in these representations. So this is my Dirac operator. Now, what restrictions does that now impose on this product? So then you get a different bimodule structure and I guess a different geometry. And I mean, this is all very new for me. So I've only just constructed these things in the last like 4 months or something. So yeah, I don't know. I've given you the examples that I have basically. So yeah, if you wanted to construct, if you wanted to start with the exceptional Jordan case and build geometries which have charged Higgs fields, it's probably possible, but then it would place restrictions on what the bimodule product is. And that's sort of it changes the way that things transform with respect to one another, I guess, in your language. But so this is essentially what I did here in the octonionic case. So what I did here is I said, I want my Dirac operator to sit in one of these, representations, the 0, 0 and the 7, 7, say, and then what products are compatible with that choice. And here is a choice which is compatible. I don't know if this is the only choice, but it's one that is compatible. Or you can go the other way around and you can say, I'm going to choose this choice of bimodule product and then try to derive the form of the Dirac operator and the sorts of fields that are possible in the geometry. Yeah, so there's this coupling that's quite nice that is very new in the non-associative case that you don't really see so much in the associative setup.
Okay, thank you. Yeah.
Thank you. Shane, from the point of view of the standard model, perhaps E6 cross E6 might be more interesting than F4 cross F4. because complex octonions give representations of standard model fermions. So I just wanted to clarify, that's usually sometimes also called the complexified exceptional Jordan algebra. So if, is that the same as a Bayesian algebra? I'm trying to understand what new feature arises when you go to C cross O as opposed to just the octonions.
Yeah, so the Bayesian algebra is a real eight-dimensional algebra. It has a very disgusting product. It's not very pretty in terms of the product. It's very similar to the octonions in that it's an eight-dimensional norm division algebra, which is non-associative and non-commutative. But it has a quartic norm rather than a quadratic norm.
Oh, but do I need to go there for E6 cross E6? I would like to stay with your framework.
Yeah, so if you wanted to go E6 cross E6, the simplest way to get there would be to take two copies of the Brown algebra, which is so what the Brown algebra is. You can think of a matrix algebra which is a 2 by 2 matrix, but where the components are the off-diagonal elements are exceptional Jordan algebra elements, and the diagonal elements are real elements.
Right.
And you can place various restrictions. There's a particular product you need to put on that vector space, and depending on the particular properties, as far as I understand, you either get E7 or E6 as the representations of that algebra, and yeah. So it's very different to the Bayesian algebra. The Bayesian algebra is a very small algebra. And it has very small representations, and its symmetry group is SU2 cross U1. The Brown algebra is a much larger algebra. They're like I don't know, like what is this? It's like 60-dimensional algebra. It's 60-dimensional. It's got 60 basis elements. They're linearly independent from one another. So it's a much bigger algebra than the Bayesian algebra. They're not really related.
What I was thinking was, suppose I have to represent 3 generations of standard model fermions. I would take J3 C cross O, put the off-diagonal elements as C cross O and their conjugates, and the diagonal elements can be real. So, and then just stick to whatever you have told us today. Would something be not okay? That's what I'm trying to understand. I want to stick to the language of the exceptional Jordan algebra, but work with C cross O.
Uh, so I don't know enough about the algebra, but presumably, as long as you can still define a representation of that algebra on itself, for instance, and as long as you have some notion of an inner product for the representation space, presumably everything should pass through. The particular examples I chose them not because I think F4 is the symmetry of nature or something like this. I chose them because I know that the mathematical side is sound. So I understand how to construct, or I have a very intuitive picture of what these spaces look like in terms of the topology. I understand what those things look like, both in the special Jordan case and the Octonian case and the exceptional Jordan case. When you go to things like the Brown algebra, I don't really have a good picture. I don't have a good intuitive picture. So I just started off with things that I knew didn't have problems. That doesn't mean there are problems in these more general cases, but I just haven't looked at them yet. But presumably everything goes through.
Okay, great. Thanks for the clarification. Yes, that's very valuable. Yes. Thank you. Any more questions, please? Did you get to discuss all this with someone, Shane and Latham or someone else? I'm very interested that these are very interesting developments.
So I should have mentioned that actually. So a lot of the early work was done with Latham Boyle. So we worked out how to construct the symmetries, the representations of the algebra on the Hilbert space. We were looking at restrictions on Dirac operators. So many of the sort of the elements of non-associative geometry were set up together with Latham, but what was missing was the construction of forms. So we were focused mainly on the construction of the standard model and non-associative analogs of the standard model, and so later on, together with Fabien Bernard, I completed, well, I did the bulk of the work on the special Jordan algebra case. And more recently, I did the exceptional Jordan algebra case and the Octonian case. So I'd basically been sitting on this stuff for a couple of years, but I didn't have a job at the time. So I was out of research for a couple of years. And so I basically sat on these results. And then I got a position with Felix Finster for a year. And so I put the time into to construct these things finally and put them together. There is so much low-hanging fruit in this area. There's also a very interesting story for how you get the three generations that's not related to the exceptional Jordan algebra that pops out of this, but that's for another talk.
Yeah, but no, I would be curious if you say two lines about three fermion generations. But my talk the next talk that I'll be giving is on three generations and the exceptional complexified exceptional Jordan algebra. So I'm very curious. Could you please say a little more what you meant?
I'm still writing it up.
Okay. Okay. It's work in progress. Great. Very good.
It's very pretty though. It's very pretty though.
Yeah. Great. Yeah, I think it's related to octonionic triality. But anyway, I wait for your work. Yes, great. And what about something like E8 cross E8 doesn't have a matrix algebra representation like E6 cross E6 does. So, do you have any thoughts on what would happen if you went to E8 cross E8?
Yeah, so E8 cross E8 is difficult because now someone can correct me here. I don't know. Maybe I'm wrong here, but I think, as far as I understand, the only algebra that has E8 as its symmetry is the Lie algebra of E8. So you would end up, as far as I understand, having like a model constructed in terms of Lie algebras. I don't know if that's problematic. I haven't explored that direction.
My picture of late has been it's best to work with E8 by first branching it as SU3 cross E6, and all is good with E6, and then one has to understand what is that SU3 doing. For me, it has something to do with space-time, like you made these two copies of psi L and psi R. I want to have them sitting on two copies of 4D space-times. So one 4D spacetime for psi L, another 4D spacetime for psi R. And then in this nice sense that you described, like the Higgs, these two 4D spacetimes are talking to each other, and both are actually part of physical reality. Anyway, that's an aside. I think Bernd said something. Do you know the Freudenthal-Tritz construction? Yeah, is that a question for Shane, Bernd?
Oh, sorry. Or the Freudenthal magic square. So there's a construction to get E8, and there was, I think, 23 years ago.
That is F4 cross F4. Yeah.
I think 23 years ago there. No, it's not. The Freudenthal magic square gets you all of the exceptional Lie groups and.
Yeah. Yes.
And I mean, I think John Bates in 2002 had the idea that maybe you get E8 out of the 3x3 Hermitian matrices over the octo-octonions. So you form a tensor product of the octonions themselves, and then you form matrices, so also kind of Hermitian matrices.
Yeah. I think that Tavian also says that. I think he's left today. He was there. SU3 O cross O.
Sorry?
So I'm familiar with the magic square construction, but generally in these constructions, the standard setup is that you want an algebra and you're looking at the automorphisms of that algebra to get the symmetry group, or the symmetries of the analogous symmetries of the representation. Whereas in the magic square construction, it's very different, right? It's not the automorphisms of some algebra; it's some other
And
some other
it's a you use derivations and automorphism to get something more complicated. Yes. So, I mean, I think it's really an open question. So we know that we get E6 if you complexify the octonions and then form a Jordan algebra out of 3×3 matrices over the complex octonions. And I think it's still conjecture. I don't know whether this has been proven that you might get E7 and E8 as automorphisms groups of 3×3 Hermitian matrices over the, well, quaternionic octonions for E7 and octo-octonions for E8. So this would be a real automorphism.
That's Tavian, Robert Wilson, Corinne Minogue for the last few years. I wish Tavian was here, but yeah.
Unfortunately, okay, maybe I should drop him an email and ask him whether this has now been proven. But this would be an example where you have E8 as an automorphism group of an algebra, or E7 as well. Unfortunately, he's not here. This is really a pity. I mean, he could just jump in and explain everything.
No, Tavian was attending, but I think he has left.
I will drop him an email and ask him what the status is, and I will keep you in line. So I will write this email to him and to you, and also to Mr. Farnsworth. So yeah, I think it's the best way to do it. Okay.
Great. Sounds great. Yeah. So any insights about the standard model using your new results for the Dirac operator is something maybe we'll know when we see your paper come out. Yes.
I mean, there's some older work together with Latham and also with Fabien Bernard, which is that you can construct mild extensions of the standard model in the special Jordan case. And in that case, you solve problems that arise in the associative case, the associative construction of the model. So if you start with an associative algebra and you look at its symmetries, and you compare those to the symmetries of the corresponding Jordan algebra, what you find is that the generators, the trace of the generators drops out in the special Jordan case. And there's this problem in noncommutative geometry in the associative setting where you get trace elements of your generators for your symmetry in the model that generate symmetries that you don't want. So like you get additional U1s which are anomalous, and you have to explain why they disappear in the standard model construction in Cons and Macaulay's and Chomsky. Like this construction, you have to impose what's called the unimodularity condition to remove unwanted U1 fields. If you construct the special Jordan analog, the generators, they're constructed as commutators, and the trace terms just drop out. You don't get these anomalous terms. There are a few things like this that are nicer in the special Jordan case. The other place where this is very the special Jordan algebras are very useful is that when you try to construct associative, this is getting off topic, but what happens when you construct the geometry of the standard model is you have the internal space and the external space. And the external space, if you look at the Hilbert space, you have left-handed fields, right-handed fields, particles, and antiparticles. And if you look at the internal space, you also have left-handed, right-handed particle and antiparticle states. And to form the full geometry, you take the tensor product. But because these states are being accounted for in both the external and the internal geometry, when you take that product, you end up with a quadrupling problem. You get too many fermions. And so one way of removing those fermions, John Barrett was here in the discussion. He has this really beautiful paper from 2006, where he suggests that what you should do is simultaneously impose Weil and Majorana conditions on the Hilbert space of the standard model, and so that you have this J operator similar to the J operator I've shown here, and you have a Z2 grading. You impose the condition J psi J equals, sorry, J psi equals psi, and gamma psi equals psi, where gamma is your grading operator, and that restricts the number of degrees of freedom down to what you actually see in experiment. But J doesn't commute with the associative algebra. And the result of that is so you start with an associative algebra and a representation of that algebra that's associative, and you see that you get too many fields. You get fields that are not experimentally observed, and so then you restrict to the experimentally observed fields by imposing various conditions, and that restricted set of fields is no longer closed under the algebra, so it no longer forms a representation under the algebra. And so you end up, what you find out is that the standard model fields, fermions, are not compatible with the associative algebra of the standard model. But what you can do is you can replace the representation of your algebra with a symmetrized action of just the Hermitian elements in the algebra, and that the algebra of Hermitian elements is compatible with the standard model.
Starting from the non-associative case or the associative?
Yeah, so that will be a special Jordan algebra. So if you look at the fermions of the standard model and you impose a Majorana condition, J psi equals psi, what you'll find is that those Majorana fermions are no longer closed under the action of the associative algebra, but they are closed under the Jordan algebra you can construct from that algebra.
Very nice, very interesting. Yes.
So that was a paper with Latham from like 2020, something like this. It was based on work by John Barrett, who was here in the talk. And yeah, that's a very nice use of the non-associative setup.
Very nice. Yes. I didn't realize that was John Barrett because the name said Thomas something, so I didn't recognize. That was John Barrett, right? You're right. Yeah, he asked you a question early during the talk. Yes.
Yeah.
Right. Great. Yeah. Maybe if you could kindly stop sharing your slides so that we can see everybody on the screen. And great. Any more comments, please? Michael? I think Michael's probably not there right now. All right. So
sorry, I was muted. Forgive me.
Yeah, please. Yeah.
Yes. No, that was absolutely fascinating. That there was a great deal to absorb.
Yeah, great. Yeah, Claudio says he's at a conference. Claudio's at a conference. Yeah. Yeah. All right. Yeah.
Well, thank you everyone for coming along.
Yeah.
And for the invite. If you have any questions, you can contact me.
Yeah. I forgot to ask you, Shane, are the non-commutative geometry people from Cohn's part of the world, have they been interested in the non-associative case?
No.
I'm curious. The mathematicians mostly have stayed away from it, right? They somehow don't like the octonions or...
so it's partially... There are people in the non-commutative geometry space that are into it. So there's people like Michel de Boisviolet. He's very interested in the geometry of the exceptional Jordan algebra.
Yes.
There's people like John Barrett who are interested in the special Jordan case. There's a little bit of interest from people like Fedele Lizzi and Andre Chitage and various other people. There's like Pierre Martinetti. There's a little bit of interest. But I think so. I tried to So I tried to build these things for a long time,
Mhm.
uh, unsuccessfully. And one of the reasons why I was unsuccessful is because there's a standard definition of the representation of representations of non-associative algebras. And if you take the standard definition, it's too restrictive.
Mm.
And so I was trying to force non-associative geometry into the standard definitions of non-associative representations. And if you
Mm.
remember that representation I had for the octonions, that product is really pretty wild.
Yes,
Yeah,
it has
right?
a lot of extra terms, yes.
Yeah,
Left and right, yes.
that's right. And so if you stick to the usual definition of bimodules, your one forms should be bimodules over your algebra. And if you take the standard definition, you exclude all the interesting geometries. And so what was happening was for many years, I was trying to build these objects under the constraint that of the usual definition of I mean, very clever mathematicians came up with these definitions, right? And I trusted them that these were sensible definitions, and they just weren't. And
Mm.
so it took me a long time to just drop the standard definition of non-associative
Right,
bimodules. And so
right.
that sort of held the construction up for some years.
Mm.
Uh, and I mean, in hindsight, when you look at the talk and you look at what is there, it's you can, if you just drop that condition, everything just falls out very easily. You can
Yeah.
build these things very easily, and there's no real obstruction. But so that created a problem in that for years, I was turning up to talks on
Mm.
non-associative geometry and giving talks on non-associative geometry, and people would always ask me, "Do you have an example?" And I think people sort of lost patience with me,
Mm.
um, and so and then the other problem was the main examples that we had of things that we could do with things like the special Jordan algebras, and
Mm.
special Jordan algebras are so closely related to the associative case that people
Mm.
just thought, oh, it's not interesting. It's you're just symmetrizing the models.
Mm.
But I think it's naive to think that way. They are actually very interesting, and there are differences between the special Jordan case and the associative case that are very interesting.
Mhm.
But anyway, so the short story is the actual examples I have are very new. Like
Mm.
the paper, I mean, the stuff I'm talking about right now, I wrote within the last few months. So
Right.
yeah, I don't really know what the general
Mhm.
view is
I was
on it.
also remembering, thank you, this the 1939 paper, Jordan, Wigner, and von Neumann, showing that Jordan algebras can be related to the standard Heisenberg algebras in quantum mechanics, except for the exceptional Jordan algebra case. So maybe, I don't know whether what you found relates to the picture, because this is, you have to do something special to the Dirac operator, right? To get things going, to have your what did you call it? The derivation.
Mhm. Yeah, yeah. So the whole construction, the key take home messages are that you have a Dirac operator, which is just an operator. It's nothing special. It's just a
Mm.
linear operator. And your one forms act as a bimodule over your zero forms. Your zero forms are just elements of your algebra. And you have to define what it means for that bimodule to be a bimodule over the algebra. You have to define the product between zero forms and one forms. And you need the Dirac operator to satisfy a Leibniz rule. And those two conditions together are very restrictive in the
Mm.
non-associative setup. And so
Yes.
and so the problem was always first of all, I had the wrong definition for a bimodule over non-associative algebras. It was too restrictive. And it's very hard to find. So if you look at the exceptional symmetries, they're very weird. They sort of shouldn't exist. You have infinite families of symmetry groups, of the Lie groups, and then you have these 5 weird symmetries that just by chance work, right? It's
They
just,
work because of triality, perhaps.
well, no, I mean, you can construct if you construct the Dinkin diagrams from, so you can, there's this nice geometric picture of the groups, written in terms of Dinkin diagrams, and there's a nice, I forget what it's called, but you can sort of plot these root diagrams.
Mhm.
And if you look at the exceptional groups, they really are exceptional in the sense that you have these root diagrams, and just by sheer luck, these root diagrams pop into existence that don't belong to any of the other families of root diagrams, and it's just a pure geometric thing. And
Yeah.
these
What I
symmetries.
understand, sorry, I'm excited. What I understand from Pierre Ramon's, famous papers from 1970, that it has all to do with spinate and octonionic triality, which allows these exceptional algebras to be Lie algebras. I mean, go ahead.
Yeah,
Go
so
ahead.
there might be yeah, I'm not familiar with those, but yeah, there might be a description in terms of triality, and there probably is. I'm not familiar with it and what Ramon says, but the point I wanted to get across is that these exceptional cases really are exceptional cases, and the algebras that are associated to them are kind of very tightly constrained. It's the product on the octonions is very special. You can't start with the octonions and add another basis element, and you know what I mean. Like, so with the matrix algebras, you can start with the 3x3 matrix algebras, and you can embed them in the 4x4 matrix algebras, and embed them in the 6x6. Right? There are this whole family, and that you can. There's not the same sort of constraint that ties everything together. With the octonions, the algebra really is sort of like this very tightly constrained object that you can't tweak in any way to get something
But
that's
this is probably also related to when you look at projective geometries, octonions don't allow anything beyond OP2, the octonionic projective plane. That fact is, I think, related to why you can't go beyond the 3x3 case. That's correct, right, Bernd? Yeah.
Yes, it is. This is quite interesting. Sorry, may I talk? I don't want to interrupt.
Yeah.
Okay, this is quite an interesting finding of Jordan, Wigner, and von Neumann. If you look at the octonion projective plane, it does not satisfy a certain axiom of projective geometry. And now I will badly mispronounce his name. The axiom of Desargues.
Mofang, I think.
Mofang plane is the octonionic projective plane, which does not satisfy the little theorem of it was a French mathematician in the 17th century, Desargues.
Desargues.
So and
who was that, Michael?
Michael, maybe you can.
No, it's Desargues. It's Desargues.
Desargues, yes.
The interesting thing about this theorem, well, there's a little and a large theorem.
No, Desargues. How do you say it?
Desargues.
Desargues. Thank you for helping me out with my very bad French. So, and the fascinating thing is that the theorem of Desargues is not an independent theorem for higher dimensions. It follows from the axioms of projective geometry for starting with dimension number 3. So if you have a plane which does not satisfy these axioms, then you cannot extend it to a higher dimension, because in higher dimensions, the theorem follows from all of the other theorems. So this means that you don't have
non-associativity conflicts with Desargues' requirements.
Yes, exactly because of the non-associativity that you have in the octonion. This is quite interesting. You also have another theorem called Pappus theorem, which does not work for the quaternions because they're non-commutative. And the octonions are non-commutative and non-associative, so they don't satisfy the Pappus theorem and the Desarguian theorem. But this means that, well, projective geometry for the octonions ends in plane geometry. You cannot extend them to higher geometries. And this is also quite strange because, I mean, if you look at finite-dimensional matrix geometries over, well, an associative division ring, you always can form kind of projective geometries with this finite dimensional matrix algebras, and you can extend this then to, well, for complex matrices to Hilbert spaces. But in a sense, you don't have a natural geometry for the octonions if you go beyond the case of 3 times 3 Hermitian matrices. You can also explain this because if you look at on the algebraic level, pure states correspond to points. I think this is also some of the findings from noncommutative geometries. And this is something which Jordan found out. And for higher dimensional Hermitian matrices over the octonions, you no longer have any pure states. You lose and so you cannot form any geometry because you lose the concept of points. So I mean, okay, non-commutative geometry is also pointless in the sense that the space-time manifold loses its point-line structure, but you still have a kind of point-like geometry in the background for the state space. And this is completely lost if you go to the higher dimensional octonion ionic matrix spaces. They're completely pointless. They don't even have a point for the state space, so to speak.
But this is why I mentioned that I started with the exceptional Jordan algebra, right? Because you do have this geometric picture, this topological picture.
Topological,
you have a nice notion of states, pure states in this case.
And for the higher, I mean, they're quite bizarre, so to speak. I mean, you could still work with density matrices, maybe to get some, but
I think it's all quite profound that nature has just gone and chosen the last end of the whole series of matrix algebras and taken the most exceptional one and maybe put it to use.
Maybe it is
like that.
I would have a follow-up question because we're now at this point to Shane. What's your view on space-time? So at the moment you have this, I think one can call them almost associative geometries where you put a finite dimensional non-associative geometry to the space-time manifold, or you have this two-sheeted space-time. But maybe this is the reason why the people from the non-commutative geometry community are a little bit silent. The ultimate goal would also to have a kind of non-commutative geometry for the whole of space-time, not only for the internal symmetries. And how will this, is there kind of roadblock for the non-associative case because, well, it ends with the 3 times 3.
My suggestion, Bernd, is to go from E6 cross E6 to E8 cross E8. I think that's where it helps bring space-time in a non-commutative sense. But Shane, that question was for you. Sorry.
I think so. The construction that people use to build the non-commutative standard model is very conservative in the sense that they just take a standard compact Riemannian spin geometry as the external space, and they take the product of that space with an internal space. So ultimately, what you want to do probably is to replace the external space with some other structure. I've been focusing on the internal space, so I don't have an answer to what that would look like. But my presumption is that the standard Riemannian geometry will break down in some way that I don't know and I don't understand.
Okay.
Yeah, I think Claudio has a remark.
He cannot talk.
Can answer this space-time question, but Shane still has to approve my construction, though.
I approve all of your constructions.
So I think
Claudio cannot speak.
Yes, Claudio, who cannot talk. This is really so.
You can talk now? No, you can't talk.
You talk now? You can still not talk.
No, he's in a conference. He's in a conference.
I actually have to leave though.
Yeah. Let's close it here. Let's close it.
Can I say one thing though, which was just to close off my remark, which is that the constrained feature of non-associative algebras, like the exceptional Jordan algebra and the octonions, is the reason why they're so difficult to implement in non-associative geometry. It's because in the case where you're just dealing with matrix algebras, you can always embed the 2x2 matrices in the 4x4 matrices. And if you look at the construction, you have in Con's models, the internal space is just matrix algebras embedded in larger matrix algebras. And because you don't have that construction in general in the non-associative case, it's very hard to build these things. And it's all to do with how constrained the objects are that you're dealing with. So anyway, I'll leave it at that. Thank you everyone who came along and found this interesting. Please have a look at the stuff. There's a lot of low-hanging fruit. So, very easy papers to write coming out of this.
Yeah, but I think one has to have your kind of expertise, Shane. One can't jump in just like that.
There's the papers. The papers say it all.
Yeah, great. Okay, great. Thank you all. Michael, we close it
No,
now?
just to say again, thank you very much. I dare say that last 10-minute burst of discussion was very exciting. I suddenly started getting glimpses of whole additional bits of the landscape, which I had not.
Yeah,
I did have a question.
we are blessed with very insightful lectures and new things. So
Fantastic. Very, very much in the OSMU tradition. Thank you very, very much indeed, Shane. That was truly fascinating. I had a question. I did actually have a question about a possible connection on the side of Clifford algebras, but it's too ill formulated even to put it. But I'll try and get it into shape and write to you.
Okay.
There
are some very interesting connections there.
Possibly to connect with a clue coming from Bott periodicity, but let me think through it.
Okay.
Fascinating stuff. Thank you very much. Terrific talk.
Thanks. See you later, guys.
Come again when you've done a bit more work on this stuff. We would love to hear the next chapter.
I will.
Thank you. Great.
See everyone. Enjoy the rest of your weekend.
Right. Thank you again very much indeed. All the best. And before we go to Jinder, we're looking forward very much indeed to hearing your latest thoughts. And
thank you.
2 weeks from now, on the 19th of September.
Yes.
Just in case anybody hasn't got it in their diary.
I'm fortunate because Shane talked about exceptional Jordan algebra, so I can take on from there. But mine is more numerical, trying out with mass ratios and stuff. But I'm very happy that today was about the exceptional Jordan algebra.
Well, Bernd will certainly have something to say about the exceptional Jordan algebras.
He knows a lot. He knows a lot. He knows a lot.
So,
I'm looking forward to
very much hearing you from on the 19th, and you're going to check up with Abe.
Yes. Thanks for
you can definitely do it on the 3rd. Okay, I think we're off.
I think of Bernd as a modern day representative of Jordan. If anyone knows about
I'm
Jordan,
the latest incarnation.
Yes. I think certainly as far as the mathematical brilliance is concerned, not I hope as far as the politics are concerned.
Yes.
Not I hope as far as the politics are concerned.
Hopefully not.
In every other respect.
Did you read the PhD thesis of Ryan Dan?
Say again?
That's a wonderful PhD thesis from 2019 on Jordan's politics, and Ryan Dan did a really good job into reading the political writings of Jordan in the 1930s, who he wrote under a false name, and he really was into this really hardcore Nazi journals like Blood and Soil, and he really did write incredibly nasty stuff.
Well, yeah, I know. That's why I say it.
It was not quite clear to me how anti-Semitic Jordan actually was.
We can separate it from the science.
Yes, of course, but
let's not open this particular can of worms.
Sorry, but I'm still
even in 1939, Wigner and von Neumann published that famous.
This is quite strange because this is always kind of strange state of mind, because at the same time he was collaborating with Jews, he was writing how bad the Jews are and that they should be eliminated from the soil of the earth. This is really strange to me.
Yeah.
So one only has to think of obviously also the collaboration, well, not direct collaboration.
That must have been quite a strange collaboration.
Anyway, look, but I do look forward enormously to your talk, and I hope also to Abe's. So I think we've got off to an extremely good start for the second half of the OSMU 2025. In fact, we couldn't possibly have had a better start to the second half.
Yeah, great.
So thanks very much again to Shane and to everybody.
Yeah, bye everybody. I'll log out
now. Nothing else you need to say, Tajinder?
No, I'm good. Yeah, all good.
Right. Okay. In that case, I'll close us down and see you all on the 19th. Take good care and support our funder, please. Okay. Thank you. Sorry, I'm afraid, but I have to be shameless about these
And
things.
I promise I will never talk about Jordan's politics again. Promise.
Oh no. It's quite a good. I'd be fascinated to talk to you another time, perhaps off piste, as it were. Okay. Take care. Very much. Look forward to
See
seeing
you
you
in
all.
14 days.
All the very best. Cheers.